Alright, so we're continuing going through all the FRQs, which we're pretty much doing in both of our classes now. To be honest, I'm not sure what we're going to do after this, because we're running out of AP problems. And we don't really have any content left to teach. Okay, so we're going to kind of combine a lot of principles that we've covered over the past couple weeks. So translational, rotational energy, momentum, spring potential energy in a new situation. And before I do, I'm going to quickly review our collisions. So what's the key difference between an elastic collision and an inelastic collision?
Elastic kinetic energy is also conserved. Inelastic, no.
Okay, so I'm going to say energy and momentum are conserved versus only momentum is conserved. Okay, cool. So here I've got a cart. The actual block of wood of the cart is mass m, but it has 4 tires, each of which are m over 4. So that means my total mass of the cart tire system for that total mass of the cart and all of its tires is going to be 2m. Okay, the disk has a radius of r. Each tire may be considered a disk. We're given the rotational inertia. Where m is the mass and l is the radius of the disk. And the cart is released from rest, rolls without slipping from the top of the inclined plane of height h, and I want to express all answers in terms of the given quantities and fundamental constants. Okay, first one, determine the rotational inertia of all of the tires. So what do I have to do?
So 1/2 tire is m over 4, so 1/2 1/2 m over 4
Capital M or lowercase m?
lowercase m L square
L squared. Okay, that would be 1 tire
times 4,
times 4
which is the same.
times 4. It would be the same, except again, this is a capital M and this is a lowercase m. So that's 1/2 lowercase m L squared. Okay, and this was our total rotational inertia. Okay, that should be good. Then part B, determine the speed of the cart when it reaches the bottom of the incline.
So that's mgh equals 1/2 mv squared.
Okay, what's our total m first?
2m.
Okay, so what should the potential energy be?
2mgh.
2 lowercase mgh, okay, equals
1/2 2mv squared.
Okay.
So 2 cancels out there, and then
hold on. So we got one more thing happening with our energy.
plus 1/2 I omega squared.
Okay. omega squared. Okay, so I'm going to need to sub in for that I. And we can get rid of those 2's that you wanted to get rid of. So this is 2mgh is equal to lowercase mv squared. And then what's my I?
Is 1/2 ml squared. Big ml squared.
Okay, plus 1/2. Okay, L is the radius of the disk. My radius is R. So I'm going to sub for that. This is, you said ml squared?
Mm-hmm.
W squared, that L is R, so this is, I'm going to rewrite 2gh v squared plus 1/2 mr squared w squared.
Mm-hmm.
Okay, is there anything that I could simplify?
Isn't it 1/4?
Yes, so I've got a 1/2 for both that part in the inside. Okay, so this is 1/2 and 1/2. I was thinking I had the 1/2 because I saw it out there, but you're right. Okay, what else?
M cancels out,
Okay, M will cancel out. What else?
and omega square is V over R
Right.
square. Oh.
Okay. So this should be 2gh is equal to
V square plus 5 plus 1/2 V square.
sorry, v squared plus, say it one more time.
1/4 V square.
Okay, v squared over 4. When I combine those, what do I get?
5 V square over 4.
Okay, and solve for v.
So V is square root 8gh over 5.
Okay, cool. We didn't have any units given to us, so I'm just going to leave it like that. Okay, and then part C. We're rolling down the incline, and the cart collides with a bumper of negligible mass attached to an ideal spring, which has a spring constant K. I want to determine the displacement of the spring, that it's compressed before the cart and the bumper come to rest.
So 1/2 L 2 MGA is equal to 1/2 kx squared.
Okay, 1/2 kx squared is equal to 2mgh. Okay, that's perfect. So this would be ideally all of the energy that we had in the beginning should be equal to all of our energy at the end, right?
Yes.
Okay, and we are solving for the displacement.
So that's 4 mgh. 4 mgh divided by k square root.
4mgh over k underneath the roots is our displacement, which we
Yes.
can simplify a little bit.
Oh, 2 comes out.
Okay, 2 roots mgh over k. That looks good.
Mm-hmm.
Okay, last one. Bumper has a non-negligible mass. After the collision, the spring is compressed to a maximum distance of about 90% of the value we just found. Why is it only 90% of the value we just found? So why was it not displaced by this much?
Because of friction?
Not because of friction.
Hmm. Mm,
What type of collision is this?
oh, inelastic.
It's an inelastic collision, so why is that important?
So kinetic energy is not conserved.
Right. Okay. Um, so if we're not losing energy, if this is an inelastic collision, then kinetic energy is not going to be conserved regardless of friction. So what else could we be losing energy to if it's not friction?
Sound?
Okay, so maybe sound. What else?
Heat.
Heat, yeah, maybe. So the collision is inelastic,
Mm-hmm.
and therefore, what can we conclude? I think you told me already.
Hmm?
What can we conclude? The collision is inelastic, and therefore what?
Kin- Kinetic energy is not conserved. And yeah, isn't it? Yeah.
Okay. Um, which would result in a less than ideal
Mm-hmm. It
velocity.
is less than.
Okay, so it
Because
could be losing the sound, could be losing the heat, but for whatever reason, um, we're not going to have that full amount of velocity that we would have in a perfect ideal world, because our collision is inelastic.
yes.
Anytime you've got any kind of deformation, so this shape kind of molds into the other, then we're going to lose some energy due to that deformation as well.
Mm-hmm.
So sound, heat, deformation. But importantly, not friction. Because friction is going
Okay.
to exist regardless of whether we're elastic or inelastic. Okay, any questions on this one?
Nope.
Okay, so I've got the rest of these free response questions from that year for the classwork and homework today.
Mm-hmm.
Um, any questions on anything from today? Oh, let me check our scoring guides really quick. We'll see how I did too. Get this on the same screen. There we go. Okay, so for the first one, 2 points determining rotational energy for each tire.
Uh-huh.
correct rotational energy for all tires. Okay, we got that.
Mm-hmm.
We did not substitute for L. I don't know if they were looking for that or not. Was there anything in the question that said we had to? In terms of given quantities and fundamental constants.
Then we don't need to, I think.
I'm not sure. Given quantities and fundamental constants. L is not a fundamental constant. And they give us L as radius. I don't think it would matter, but... So we did go back and change that for the next one. But I'm going to give it to us. Because we had the same idea. Okay. Then... Okay, U is equal to our kinetic energy. Okay. So 2mgh equals... Okay, that's not the same method we did. But we do end up with the same result.
Mm-hmm. So it doesn't matter.
Correct expression for potential energy at the bottom. Recognizing kinetic energy is the sum of translational. Okay, we did do translational and rotational energies. We did use conservation of energy. Okay, correct translational, correct rotational. Recognition that omega is V over R. Substituting potential energy, correct solution. Okay, cool. And part C. Energy conserved. Correct expression for potential energy. Okay, solving for displacement. Okay. That's good. Then discusses the inelastic collision, loss of mechanical energy, or reduced velocity resulting in a smaller compression. Yeah, less than ideal velocity. Okay. Any questions on what we did?
Nope.
Cool. Alright, then I will see you tomorrow for CalcBC.
Bye bye.
Goodbye.